Hey Geo1B students, welcome back to another great video. This one is on circles, circumference, and area. So I'm going to talk more about area and derive the formula for area from circumference. But before we do anything, we need to go back and I want to draw your memory back to a lesson that we had several weeks ago. And here's a clip from an awesome video that Miss Shainthal made regarding spheres. And she had you think about spheres in a very particular way. And I want to use that same kind of thinking as we're talking about circles. So check this part of this video out.
This is a video from the 1950s of when we used to construct globes by hand. Looks like tough work, right? I want you to take a minute and go back to the net that you originally drew and adjust it based on these sort of pieces that these women are cutting out to form the globe. Also, the science teachers wanted me to remind you that the Earth is in fact spherical and not flat. Now, your adjusted net of the sphere should look something like this. Pretty cool, right? Now, these oblong pieces sort of fold up and meet at one point at the top, and then fold down and meet at one point on the bottom, which would...
Okay, so notice how in this video the sphere was cut into all these little segments, right? All these little pieces. And if you connect all these pieces at the very top, it forms a point at the very top, sort of the North Pole. The South Pole would be all these pieces down at the bottom. Okay, so let's use that thinking and apply it to circles. All right, so with circles, let's apply the same approach or the same thinking to the quote net of a circle. Now, the reason I put net in quotation marks is because a circle is two-dimensional, so it doesn't really have a net. A net is really taking a three-dimensional object and flattening it out into two dimensions. But we're going to use the same type of thinking as we think about circles. So we all know what a circle is. So here we have a circle, this nice circle that's just kind of minding its own business in two-dimensional space. And it's a poor nameless circle. Sorry, I didn't give it a name. But we did give it a dimension. We gave it this red radius, and its radius is equal to r. So we start with a circle with radius r. Its circumference, recall that the circumference is kind of like the perimeter of a circle, meaning if I took a circle and I snipped it at one point and I stretched it out and made it a line segment, okay, I would measure how long is that line segment. Okay, and that's the idea of a circumference. Or we likened it to a perimeter where the perimeter of a polygon is, how far is it to go all the way around the outside of the polygon? Same thing with the circumference. It's how far is it all the way around the circle. Finally, I always go back to pizza because it's one of my favorite foods. And the pizza, if you think of the crust of the pizza, the very outside of the crust, that's kind of like what I think of when I think of the circumference. We know that the formula for circumference is 2 pi r, or pi d, or d pi, right? Like the summer class is d pi, but 2 pi r. Okay, so if we take this circle, and let's say it's a pizza again, and a pizza is nice, like if you make a frozen pizza, but what do you have to do? You have to slice it. And let's say you're going to share this huge pizza with many, many, many of your friends, and so you're going to slice it into many, many, many slices. And each one of these pieces of pizza is going to be exactly congruent. Okay, so it's going to look something like this. So we've sliced this circle or this pizza into many, many exactly congruent slices of pizza. And each one of these is a radius. Okay, so we sliced it, we cut it very, very carefully. And the circumference we know is still 2 pi r, right? So now what can we do with this sliced pizza? Well, let's think about what area is. The area of a two-dimensional object is basically how much space is that object taking up, right, in two-dimensional space. So how much space is this pizza taking up? Well, how much space is it taking up? That's what we're going to figure out right now. So let's rearrange all these slices of pizza and let's make them approximate a parallelogram. Okay, so now we take out all the slices and now we lay them this way, and now this approximates a parallelogram. And the only thing that really is not parallelogramish about this thing is that these little pieces, this part of the crust, these are curved a little bit. If those were straight, this would be indeed a parallelogram, okay, but those are curved. And if you think about this for a moment, if I made many slices, okay, if I made a lot more slices, each one of these curved parts, okay, would become smaller and smaller and smaller, right? And in fact, if I made so many slices that it approached infinity, like I made infinite number of slices, then it really would take up the same amount of space as as an actual parallelogram. And this kind of thinking is really important in future math classes like pre-calculus and calculus, where you talk about as something approaches infinity, then what happens? Or taking a shape and slicing it into many small sort of slivers. Okay, these are a couple of the big ideas in calculus, the idea of limits and the idea of what's called integrals, but you'll get to that later. So isn't that great? You guys are already learning to start to think like calculus students. Okay, so we want to know, we have this shape and we want to know what is the area of this shape, this almost parallelogram. Well, the area of an actual parallelogram is really nice. It's just base times height, right? We learned that a long time ago. The area of a parallelogram is kind of the same as the area of a rectangle, and it's just base times height. So what is the height of this thing? The height of this thing is r, right? And when I first looked at this, I said, wait a second, I made a mistake. That's not r, because r is this kind of slanted part, and that can't be the same as this, because like slant height versus height. But no, those actually are the same. Why are they the same length? Because this part at the bottom is curved. So this little piece goes down like that. So the red piece is just as long as this black line segment. So the height of this thing is r. So my question is to you to think about is, how big is the base? How long is this base of this almost parallelogram? Can you figure that out? Well, it took me a while to figure it out as well. Okay. And of course, I didn't discover this. This is not, anything new. This has been around for a while. But this part down here, that's the crust. And this is also the crust. So that's crust and that's crust. So together, those form the full crust of the pizza, which is the circumference, right? So if I just look at one of these pieces down here, that base length is going to be half of the circumference. Okay, and we know that circumference is 2 pi r, so this base length is going to be half of 2 pi r, which is going to be what? Half of 2 pi r is just pi r. So what is the area of this shape? The area of a shape is the area of a parallelogram is just base times height. And the base of this thing is pi r, and the height of this thing is r. So the area of this parallelogram is pi r squared. And that also tells us that the area of a circle is equal to pi r squared. And this is the guy that discovered it. He wasn't the first one to discover it, but he's the one to prove it. And he proved it. His name is Archimedes. He proved this way back in 260 BCE. So how do we actually use this formula? Well, there's a couple different ways we can use a formula. So A and B. Here's a couple example problems. First, find the area of a circle with radius 2.5 centimeters. Well, that's easy. This is going back to like pre-algebra, right? So the area of a circle is equal to pi r squared. So write the original formula in general form. Okay, substitute in the values that we know. We're given 2.5 as the radius. Okay, so it's pi times 2.5 squared. We're only squaring the 2.5. So that gives us 6.25 pi. Leave the pi as pi, okay? Because we don't like approximations. I mean, sometimes the book is going to make you approximate, but in general, math teachers like it when you give exact answers. And then now I added the units at the end. Remember that area is two-dimensional, so we have squared units. So the area is centimeters squared. Okay. In part B, we're going to reverse engineer this or work backwards. They give you the area is 113.1. Okay, so same formula, area equals pi r squared. And now we substitute in this 113.1 for area. Okay, so 113.1 is equal to pi r squared. And what we're trying to do is get r by itself, okay, because it asks for the diameter, but we need the radius first, and then we'll just double that. Okay, so right now it's pi times r squared, so we want to get rid of this pi, so we're going to divide both sides by pi. We get 113.1 divided by pi is equal to r squared. Then we just take the square root of 113.1 divided by pi. And we're going to do all of this on our calculator. In this case, we are going to actually approximate. Okay, so we get r is equal to approximately, notice I use the squigglies, it's approximately 6 centimeters. And are we done? Did we answer the question? Nope. Go back and read the question. It asks for the diameter. So given the radius, how do we get the diameter? We just double it. So the diameter is approximately equal to 12 centimeters. Okay, that's pretty much all I have for you. Okay, don't forget to take pictures of all your work and submit it according to your teacher's instructions. Otherwise, you might not get credit. Okay, it's very important that you follow instructions. Okay, and for my classes, I have one submission document that all of your homework goes on. Okay. If you don't submit it properly, what's going to happen is teachers are going to have to open up multiple images and wait, and it makes our time for grading 5 times or 6 times or 7 times longer. So please make sure you follow the instructions. All right, I hope you enjoyed this video and enjoy your homework. And remember that if you have any questions, please post them as public comments in your Google Classroom. Stay safe, stay well, and stay indoors. Thank you.